Paul McMillan is going to talk to us about attacking the Internet of Things. Seems to be kind of a theme today, but he brought a light, so he wins. And this demo is going to go just fine for him because we had plenty of prep time. So, for the last talk of the day in Party Track, let's give a big Party Track welcome to Paul McMillan.
Okay, so I'm going to talk about timing attacks. The Internet of Things are a great place to start. I'm a security engineer at Nebula. I work on building clouds. This is not directly related to what I do for my day job other than that I do security. So we're going to talk about a number of different ways that you can, there are lots of different kinds of timing attacks. The one we're talking about today is what's called a string comparison timing attack. One of the properties of this is that it takes a while to run. So we're going to get the demo started first. And can you hear me from over here? No. One of these? Yeah, okay. So the demonstration that we're doing today is using the Philips Hue network light bulb controller. In order to demonstrate that I have nothing up my sleeves, I'm resetting the controller there and turning the lamp on. Now they're not connected, and there are no usernames or any other data in the controller here. The rest of the setup that I have here is a extension for my PCI Express bus, which allows me to run a server-grade network card attached to my laptop for the demo. We'll get to that in a little bit, why that's useful, but the most important part of it is that the network card allows me to do hardware-assisted timestamping on all the packets that come in and out of the device. So, talking about timing attacks. So, at the most basic level, asking a computer to do any operation takes time, a measurable amount of time. A timing attack exploits this by noticing differences in the amount of time it takes to process something. This is a pretty typical example of a user authentication flow. You start with getting a username and password from your attacker. You look up the hash in the database. You compare the hash you got from the hash you have in the database, and then you return. I know there's issues with this, but this is sort of the basic workflow. The obvious timing attack here is that if the user doesn't exist in the database, this will take a lot longer, or this will take a lot less time to run. So an attacker can can use this kind of a workflow to guess a bunch of users in the database, and use that to accelerate their attacks. That's not the kind of timing attack we're talking about today. And there are lots of other kinds as well. You've got blind SQL injection, you've got CPU timing cache attacks. What we're talking about today is string comparison timing attacks. So this is a pretty typical implementation of the string comparison function. I actually pulled it from the source code for the device that's sitting over here. And this is the relevant bit. The most important thing about this piece of code is that rather than comparing all of the pieces of the string together at once and saying they're the same or not as an atomic CPU operation, it starts with the first two characters in the string, first two characters in each string you're compares them. If they match, it moves on to the next two, and so on, until you either get to the end of the string or they don't match. The important behavior here is that we have a very small timing difference when you have a string which is partly correct but not all the way correct, and a string which is not correct at all. The amount of time where it either tries to do that next comparison and fails, or just stops doing the comparison, is something that we can exploit. And if you look at the properties you get out of this, what this means is that when you're trying to brute force a credential, if you can do a string comparison timing attack on it, the time it takes to run the operation goes from an exponential function to a constant function of the number of items that you have in the string. So there are a lot of, you'll see recommendations to make your passwords 10 characters long. The thing about that is adding another 2 characters to to an authentication credential that is vulnerable to a string comparison timing attack means it only takes 2 more of the constant amount of time rather than raising to another power of 2. So this is a very powerful method if you can do it. The problem is it's really hard to do. A lot of people will tell you that this is only a theoretical vulnerability. It's not actually really an issue. I kind of just explained why I think timing attacks are interesting. The drawback is they generally make a lot of noise. You have to take a lot of samples of whatever it is that you're trying to compare, whatever it is you're trying to attack, before you can make a decision, a statistical decision about whether or not the data that you have means anything. So let's talk a little bit about time. Sort of intuitively, we know that getting from San Francisco to New York takes about 70 milliseconds. We know that getting data off a spinning disk takes about 13. Going down further, RAM latency is about 83 nanoseconds. And then if you're getting the cache in the CPU, you're in the 1 nanosecond, sub-nanosecond range. And then down to the CPU cycle, which is a third of a nanosecond. By the way, the references for everything are in the speaker notes on my slides, which will be on GitHub after the talk. So go down a little further. We've got the speed of light in a network cable. In a meter, it goes about 5 nanoseconds. Takes 5 nanoseconds to move a meter. And so I'm getting lost here. So the other thing to remember when we're talking about network latency here is that usually the PCAPs that you're used to working with are generally captured in milliseconds, not nanoseconds. Wireshark will show you nanoseconds, but generally it's 0 unless you've done a bunch of work to make that not the case. So the string comparison, the timing difference that I talked about earlier it's on the order of nanoseconds of a difference, but that's on a 3 gigahertz machine. This device down here is only 120 megahertz. It's running a little embedded processor. It doesn't do multiprocessing. It is not very smart. So here's a picture of it. The way this system works is that the base controller connects via a wired connection to your network, or in this case, my attack system. And then the controller speaks the Zigbee protocol to the light bulb. At the moment, the controller isn't paired with the light bulb, so the light bulb just acts like a normal light bulb and comes on when you turn on the power. It looks like the device has finished the reset, so I'm going to go ahead and start actually attacking it. So give me a moment here. So, unfortunately, I can't show you both screens at once. What I'm doing over here is I'm starting a TCP dump session to collect the network traffic between the network card and the Hue. The important thing about that is that this is the very latest version of TCP dump, which allows you to capture nanosecond level differences if you have the hardware to support it. So once I've started the TCP dump, I'm going to also go ahead and start my data collection script. What the data collection script is, so to back up a little bit, the Hue API is very simple. It's just to access the device, you send a GET request and you put the authentication credential in the URL, and that's all there is to it. There's only one authentication credential, it's 10 characters long, and it's not hashed, it's not encrypted. And so I have a Python script here that is trying to do a whole bunch of requests to that authentication credential, starting with a set of known characters, and we're collecting data now. We're guessing the first couple characters there. So let me make sure we're actually receiving the data over here. And we're not getting that. Okay. So, sorry, this bit is kind of fiddly. Okay, so we are not getting data. Okay, so I was hoping to have this computer doing the analysis while that computer collected the data. It looks like what I'm going to have to do is analyze the data on that computer as we go. The downside to that is I can't use both CPUs. If I run the analysis on that computer, it's kind of noisy and it pollutes the data a little bit. So while we collect an initial chunk of data here, we're going to talk about network timing precision. The milliseconds you get from the kernel's default drivers are just not really what you want that you get with the default TCP dump, are not what you want for this kind of attack. The details you're looking for are, as I said earlier, in the nanosecond range, and you just are really going to lose a lot of data if all you have to work with is milliseconds. So there are lots of things that can make your data collection imprecise. Graphics drivers, you've got background networking. Basically, you want to turn as much of the machine off as you can, and then once you've verified that you can actually conduct the timing attack, then you can move it back to being a more normal system and design your parameters so that works. The other thing that is really important is using the hardware timestamping. The default software timestamping is really noisy. You're not top priority, and that's just the way it is. So the hardware that I'm using here is the Intel i350 NIC. A lot of the newer laptop drivers are starting to have precision time support. These are getting added because NTP just doesn't cut it for a lot of data center needs. The data sheet on the i350 says that it can capture at a precision of around 8 nanoseconds. I'm thinking that's probably a little bit optimistic, but it's not too far out. So I didn't put the picture in. I wanted to get the demo working more than I wanted the slides to be pretty, so I hope that doesn't bother you too much. So I already kind of explained it, but the other thing that's relevant here is that the Express card to PCI Express adapter is just the direct bus adapter. It's not a very complicated piece of hardware, so we're not going through other protocols to do that, which allows us to retain the performance that we need for the network card. So I talked through what we're doing for the data collection. And when you go to look at the code on GitHub, you'll see that it's really just a couple simple scripts that are doing individual things. The idea was to break it down, not give you a giant monolithic thing that you have to run all on the same attack machine. So we have a traffic generator, which is just repeatedly sending different variations of the guess for the next character in the authentication token to the server. We have the data collection, which is TCP dump, and then we have a separate analysis script. And then the idea was that we would feed that back through the analysis script on this machine and update the next guess as we got enough data to assume that, or to prove that we knew what the next character was. Unfortunately, I'm going to have to do that by hand because the machines aren't talking to each other. Let's see how much data we have. We're going to let that run for a little bit longer here. So things to make this work. You need at least libcap version 1.5. You need at least TCP dump 4.60. Otherwise, you don't have the hardware timestamp support, and you don't have the ability to capture at the nanosecond level. They work on Ubuntu 14.04. I haven't tried them anywhere else. And TCP dump 1.6.1 just came out like a week ago, so that's a pretty good choice. So nanoseconds turn out to be really inconvenient to work with. Scapy doesn't like to read the PCAP files. Almost everything else doesn't like the new format with nanoseconds from TCP dump either. Wireshark will read it, but Wireshark is not a generally useful packet parsing library that you can embed in other things. For better or worse, I ended up doing that, and what I'm using to parse these packets in the analysis script is a package called tshark, which is the command line version, and then a wrapper called PyShark, I think. Another thing to remember when you're working with these numbers, you can't convert them to float because you lose the precision. The easy way around this is to just work in nanoseconds and subtract a large value from every value you work with, or just deal with the differences. And the other problem is oftentimes you don't realize that you're converting things to floats if you call out to other libraries, you call out to data analysis libraries. So it's better to convert these into smaller differences when you actually want to work with them. So this is the Hue API. It's very basic. The networking stack in that thing is very interesting, and I mean that in the nicest possible way. It always returns the HTTP 200 status code. It doesn't really mind if you just don't send ACK packets. It just kind of keeps going. As I said, it's just the user token. There's no username and password, and it's not very fast. Depending on how the device is feeling on any given day, it's between 30 and 60 requests per second that I can talk to. So this is the other limiting factor. It's nice that it's slow because the timing attack we're trying to exploit is more obvious, but it's not nice because it takes a long time to collect the data. Other things about the Hue, it's running FreeRTOS 6.05. The SSD implementation, which I'm using to discover it on the network here, is pretty much someone looked at some traffic and said, oh, that must be how it works, and didn't read any of the documentation. And the behavior with the HTTP responses is very interesting. As I said before, the speed that you can get out of it is variable, and the properties that the network stack seems to have is, rather than buffering packets in some kind of a sane manner, you send a request, it gets your request, and it sends back a few hundred bytes of the response, which is always HTTP 200, doesn't even think about that. And then it cuts and makes a packet break and goes and thinks about it for a while longer. Now, anytime that it's thinking about it and constructing the rest of your response, if you send the ARP packet to that initial part of the response that it sent, it will stop processing, go back to the network stack, dump whatever's in the network buffer, send it out to you, and then go back to processing. This might make sense, this might work out well, but if your machine is a lot faster than it, you can spend most of the response time having it doing this context switch between the networking and the thing it's actually trying to do. And you get an extremely variable amount of time that the whole process takes. It's really problematic for your precision. Let's see, other things. Oh yeah, the HTTP stack basically ignores whatever headers you send it. It doesn't pay attention to content type or any of that. It sometimes sends out the wrong Ethernet frame check sequence, and it sends a lot of random stuff even when it's not connected to the internet. I've noticed that occasionally when it has an IP address, it'll still be trying to DHCP. It's always looking for open DNS even when it knows where it is. So let's go back to the principles of the attack we're doing here. And okay, so I believe we've collected about 5 minutes of data here. And so I'm going to start the first of what will be several statistical analysis on the data that we have collected. And I will show you what we're getting. So we're stopping the packet capture here because I would normally be doing it on that machine, but it's not working now. So the other thing that takes time with this process is, as I mentioned before, I can't use a normal packet parsing library because nothing supports the nanosecond timestamp magic cookie at the top of the file. So rather than building a parser by hand, I figured for the demo it was okay to use someone else's. That means that the process of converting raw packet data into something that I can parse is going through T-Shark, and then it's turning into an XML representation of the packet, and then it's parsing that XML and pulling out a few stats and then writing them back to a CSV file. This is really inefficient and ends up pegging the CPU on the machine that's doing it. I would like to do better, but I was more interested in the properties of the proof of concept than the actual time that it took to implement it. So let's talk about statistics. So the statistical things that we're going to do to the data in a minute, which I will show you, are not going to be the ones that immediately spring to mind. You can't use the t-test, and you have to be very careful because when you go reading about statistical methods, a great many of them require your data to be normal. Your data in this case is most fundamentally and assuredly nothing like normal. The distributions are banded and striated, and I'll show you what they look like in a minute. The statistical test that we're going to be using here is called the Kolmogorov-Smirnov test. And it is a test which allows us to assert, the null hypothesis is, it allows us to assert whether or not a pair of samples come from the same distribution. It doesn't allow us to say anything more about them other than whether or not they appear to be from the same or different distributions. So in this case, we're going to be, so to back up a little bit, let's talk about the Hue API. So that user token, what we're using for the user token right here is octal. It's 10 randomly chosen characters, 0 through 8. And so for our hypothesis testing, we are we're generating a random user token and starting with a guess from each of these categories. Once we've parsed the data, we sort the results that we got from each of these tests into buckets based on what the first character that we're investigating is in the string. So this means that what we're trying to do is say which of these data sets, and in this case it's going to be probably several tens of thousands of data points, which of them is different from all the other ones. And so we're trying we're trying to identify the outlier here. So, as I said before, we can't use the t-test because it requires your data to be normal. And the Kolmogorov-Smirnov test is the best one that I've found. I've tried a number of different things, and the ones identified in the literature, the Cross paper from 2009, their box test didn't work super well for my data. I'm not sure whether my data looks very different from theirs or whether they, what was going on there, but the KS test works pretty well. Where are my graphs? So, this is still parsing. So once we've collected this data, what do we do to actually prepare it for running into the algorithm? Because we can identify the timing difference by just taking all of our data, putting it into the algorithm and saying sort it out, and just collecting more samples until we get the difference we're looking for. Unfortunately, that takes a very long time. When I submitted the talk, the amount of time it took to do a single, to identify a single string that was different took me about 8 hours worth of data. I've gotten that down to about 12 minutes if the parsing works right. But unfortunately, I have to go back and forth for that. So the various ways that you can prep your data, there are a lot of ways to screw it up. If you filter your data and then you end up, so you have time series data, but but the KS test doesn't care about the time series. It's just sorting your data and dealing with it. So if you have data where you have a jump in the overall processing time for a while, and you do a linear filter, just an upper and lower bounds, you end up with samples where you have a lot of samples from a time period that is not well represented by the rest of your groups. This really screws up the statistics, and if you do that, you end up with data that just isn't useful. So the code is up in the repo, or will be. I showed you how it's separated out. The code is really a starting point for an analysis. It's not a full-blown just click it and run tool, especially not against some other device. Let me just actually show you some of this code here. So, it is right. Yeah, you're totally not going to be able to see that. That's just not a good idea. How's our analysis going? Okay, so it looks like I've about finished the initial analysis of the first round of data we gathered. So I'm going to go ahead and see if I can plug this laptop into the projector and show that to you. Okay, can you see that now? All right. So the script that we're going to do now is the calculate guesses script, which is taking the Where's our... Damn it. This was working earlier. No. Okay, well, so let's start by looking at what the process data looks like. So, this is what the data looks like after I've processed it. What these are showing is the relative differences in packet arrival times as we interrogate the unit. So if we look at the raw data with Wireshark, we can see the conversation that I was telling you about with the device here. We send a GET request, we get back this one part of a packet, and then we get back the rest of the packet, and then we have some other network connection handling. The device doesn't know how to keep the socket open, interestingly. So what we're looking at when we actually analyze the data is that we're taking the time between this first packet and the time that the rest of the packet arrived. A lot of texts will tell you look at the total time that the request response cycle takes. In this case, just the difference between those two response packets provided a much better signal. Okay, this is not. No. Okay, I don't know what's wrong with that, and I'm very frustrated. Huh? Yeah, okay, where's the drink? Yeah, so what that should have shown us, and it will immediately after the talk, I'm sure, what that should have shown us was a collection, a set of the KS test analysis for each of the combinations of the data points that we have. So we have 8 different guesses that we're trying. So we have 0 compared to 1, we have 0 compared to 2, and so on, all the combinations of the data. In general, what you see when you do that is that you're still plugged in over here. In general, what you see when you do that is that as you gather more data, the values fluctuate. And so you have a p-value from the KS statistic, but the p-value from the KS statistic is not going to be the one that you look at for the overall result you're looking for, because it's only relevant to that individual comparison. Because you're making the combination of that many comparisons, your overall p-value has to be much lower. Your overall expected p-value has to be much lower for the system. So the way that I handled choosing which one is different is I take all those p-values, pick a threshold, and say when the values are at the acceptable threshold, we count that as a vote for each of those items as being different from all the others. And what you see as you collect data, as you get up into about 10,000 packets, the thresholds start to become very obvious. You start to see that everyone is saying this one, whichever one it is different. So in general, when the system is not broken, that takes on the order of 12 minutes per character to brute force in this system. If you want to be really, really sure and not accidentally choose the wrong character, if you go up to 15 minutes, the statistical difference starts to get just ridiculously obvious. So I will get this working and post a YouTube video of it later. So we're going to go through some of the things that I learned while implementing this attack. So if you can keep the socket open, do it. Anything to reduce noise, anything to reduce the number of packets that you have while you're interacting with your target device makes your life easier. The differences you're looking for are really small. Do everything you can. Is this not presenting? Well, I'm just reading you the slides anyway, so. So when you're configuring your network parameters, use the hardware timestamps, turn off the queues and the hardware assist on your network card. Obviously use nanoseconds. And just everything you can to make everything quiet. If your device is multi-threaded, it turns out that using slow LoRa's to tie up everything except for the thing that you're trying to do works pretty well. This thing can't handle multi-threading, but in other things that I've tried it on, that helps. In this case, don't run extra stuff on your attack machine. Don't try to analyze and capture data at the same time. I probably should have done that, and then the demo might have worked. But the other thing is profile your victim. When you look at this thing, you can actually see that it has noisy periods and it has quiet periods, and you can discard the noisy periods. And the way you want to do that is by picking a time around when the noise occurs and discarding that, as opposed to just filtering values that are too high or too low. The reason you don't want to just filter values that are too high or too low is for discarding things around noisy periods is that then you end up biasing your data towards a sample that may not be relevant. Another thing that helps with this device is if you get it warm before you start. The differences are fairly small, but as it heats up, it changes, and if you don't warm it up before you start the data collection, you will have more trouble getting statistical certainty. Again, finding the simplest request possible. The device doesn't have a lot of processing power. If you shorten the length of the request you're making to it, you get better results. In this case, I took away all of the HTTP headers except for the first and second lines, and it didn't notice. Again, the most common mistake I think that I ended up making as I was working through different ways to analyze this data was accidentally making assumptions about normality. Assuming the data was normal, picking a test that assumed the data was normal, doing things that required the data to be normal. Another thing that's important is to gather data on all your hypotheses concurrently. If you gather all of the data on A, and then all of the data on B, and then all of the data on C, because they're not linked in time, you end up with sort of macro level drifts, which mean that you can't compare the data and it's completely worthless. In the code that I'm using here, it randomly resorts my array of things that I'm testing every time it cycles through them, but it doesn't just randomly pick. It does make sure that it runs each hypothesis about the same number of times. Another thing, don't overwhelm the device. If you slow down and give the device time to process the requests, you end up with less noisy data. In my case, the way I did that was by setting up my firewall to block ACK packets because they were making the data noisy. The other thing to remember about this is don't forget that you can just stop and brute force a token. You don't have to do the timing attack all the way to the end. And in a 10-character password, if you can do the first 5, the rest of it may be easy to do online brute force depending on the size of the key space. Another thing to remember is not the case in this device, but in many devices, the code will short circuit if the strings that you're comparing aren't the same length. So in this case, you know how long the authentication token is, and it's worth sending a full token with each request because some code will short circuit in that case. So I talked earlier about taking a moment to let the device, breathe between requests. Try it both ways though. Once you have the statistical tests, you can very easily tell whether the data is better or worse, and it allows you to do hypotheses testing and say, if I do this one thing, does it make my data better or worse, and then verify it, as opposed to just relying on your gut feeling. The other thing about this is it's really easy to get fooled by your own data. You'll sit there, you'll gather a bunch of data, you'll analyze it, and you go, I have a way to analyze this data that tells me the right answer, because you know what the right answer is. And then you'll write it down, you'll apply it, and then you'll go gather some more data, and you'll find out that the test that you came up with, which relied on some magic numbers and maybe a multiple of something, totally only worked for that collection of data that you had. So when in doubt, always take more samples, and take samples, analyze them, and then take more samples when you change your method. Don't assume that you have a method that works when you have the data that you have fits and gives you the results that you want. So I like this quote because I think it explains that really well. If you try hard enough, eventually statistically significant findings will emerge from any reasonably complicated data set. When results are analyzed many ways without a plan, the results simply cannot be interpreted. At best, you have to treat the findings as a hypothesis to be tested in future studies with new data. So that's the end of my slides, and it looks like I'm about out of time. So other than the non-working demo, does anyone have any questions? Yeah?
Are the tools for this online?
I'm going to make the GitHub repo with all the embarrassing code in it public as soon as I step away from the mic here. Yeah?
Does this work on a wireless network?
You would have to work very hard to make this work on a wireless network. It's probably possible. The things you would have to do to make the network cards consistent enough would require a lot more samples than what I was trying to demo today. You'd probably be looking at on the order of days worth of data to analyze a single character difference. Yeah?
So you said that there were some graphs that you had of the data plotted. Can you show us a statistically significant, the X character must be a 4, that sort of thing?
I may have misplaced all of it. That may not be here. Yeah, I don't think I have the graphs handy. Sorry. Yeah?
If you had to design a system to defend against this type of attack, make it very difficult to use, what would you do?
To design a system to defend against this kind of attack, you have to make both the correct and the incorrect paths take the same amount of time. A lot of people in response to this say, I'll just add a random amount of delay. Well, your random amount of delay has a predictable distribution, and so I just take more samples and then your random amount of delay goes away. And adding a fixed amount of delay doesn't change the statistics at all and actually makes it just about the same. So, anything else?
All right.
All right.